Welcome to an introductory video and a series about how modern vehicles have turned into simulators on wheels and how we got to this place, covering some of the technical reasons why, the evolution, and then we're going to speak with some automotive engineers that are working on some of these cars and the tools that they use and how they're trying to do their best to get new cars with all these electromechanical systems to feel like you're actually driving them, or in many cases, not driving them at all. We're going to talk with some engineers in the sim market, where oddly enough, the sim creators of hardware and software are really pushing faster and harder to make the simulation world, the cars that you don't really drive, feel more real than physical cars on the road. And it's a weird place to be in the technology world, and we're going to get right into it. Now, there's kind of two sides of this story for me personally. When I get in and out of all these newer cars, I gotta be honest, I'm over it half the time. I'd rather be inside some 90s pile that is super simple, not a ton of BS. But I have a morbid curiosity of how everything works. And instead of burying my head in the sand, I really do want to learn about the engineering and the technical side of these cars. And we're very lucky to have access to some of the best engineers in the world. From Corvette to Ferrari, Porsche, Lamborghini, Honda, Toyota, Mazda, Ford. We've talked to some of the best people. And the odd part about it is a lot of them share the same opinion about modern cars. A lot of them are like, man, it's really hard to make a new car feel like an older driving experience, something that is more connected, that all the inputs are natural, because they're working with such a wide variety of technology that has to be in place in these new cars. And I'm going to go over some of that technology now and how it's evolved. Now, first we have to understand some of the legacy technology, like my old 1998 Honda Civic DX. It had manual steering, no power steering. It had crank windows that you had to manually do it, which was a workout. It had a manual transmission, and it had no ABS, which is no analog brakes. And you realize in this world today, 25 years later, that is almost impossible to find any car. In fact, the first time Jack drove a car without ABS, his brain broke. He could not literally figure out how to even drive the car because it was locking up if you push the brake pedal too hard. So we're in an era that is like science fiction compared to that. So now modern vehicles are using a combination of those old mechanical systems that, manual steering rack and brakes, and you are now using them as electromechanical systems, which is taking the mechanical side of that, like a differential in the back that is purely mechanical, and you're adding the electronic control component to it. And when you add the electronic component to steering, adding an electric motor there, you're adding ELSDs or electric motors as differentials, you're adding brake-by-wire, you're adding steer-by-wire in some cases, it's more rare right now, and you're adding drive-by-wire, which is throttle controlled by an actuator. You need a processing unit, an ECU, or a control logic for each one of these systems. So that means that there is a computer or multiple computers inside of all these new cars that have a layer of software to get all of these systems to talk to each other. And a large part of the reason it exists is because of modern safety suites inside of cars. So lane keep assist or crash mitigation, where computer systems inside the car need to take control of the braking system, which needs an electronic actuator for the car to stop itself. It also needs to take over steering in some cars, where you need the electric motor, a certain amount of torque applied to the wheel, and the software to turn the steering wheel away from you or to stay in your lane. You need the ability to control throttle electronically, and you need to control a wide variety of the braking system in terms of corner-to-corner braking to stabilize a car in a crash or in loss of traction. Now, 15 years ago, a lot of these systems weren't possible because processing power, the compute power behind the car, wasn't fast enough to tie all of these systems together. So As we get more and more evolved, there are a lot more things that have been added, not just the steering, brakes, throttle. You now have rear steering, where the rear wheels turn along with the front. You have active suspension, where the car is righting itself. You have air suspension, where there's inflators inside of each of the shock absorber bladders to kind of load level the car. You have adaptive dampers that are changing the valving electronically. So when you start to add in all of these systems, everything has to speak to each other instantaneously to make sure that when you drive, it doesn't feel like 10 different things are going on. It has to be immediate. And that immediacy is not just hardware. It's how the engineers control all the software and how everything talks to each other. And when you start adding up all these systems, along with the safety protocols of, when do you detect a crash? When do you come in and interfere with the driver? I mean, it's no wonder why these cars are so complicated. But when we talk about electromechanical systems, that's the challenge of the modern vehicle. Now, there is a big difference between electric vehicles and internal combustion, because the responsiveness of an internal combustion engine and a standard mechanical differential doesn't need the crazy control that an electric car would. Electric motors are instantaneous. You can pulse it on and off faster than you can do controls on a gasoline engine. So the speed at which electric cars need to do processing for all those systems I just talked about is even more extreme. So that changes the car's network of how each one of these components talk to each other. Traditionally, a lot of legacy cars have all communicated through a CAN bus system, where it is all communicating over a link, but that is bandwidth limited. Like, think about your internet connection at home to the internet. If you have a slow internet connection, it takes a lot longer for something to download, or there's more latency between doing one thing or the other. Same thing goes in a car, depending on the network. When you're dealing with some of these most extreme systems, in the case of very, very modern electric cars, all of that data needs to go across this network, and it can't be bogged down by speed or about the amount of data that's passed. So a lot of modern cars now are moving to Ethernet, basically a giant network inside the car over Ethernet at a higher link speed with lower latency. So now all these systems can talk together even faster, and a lot of this is going to be a massive requirement for autonomous cars when you get to level 3 and 4. You can't have any hiccups in not only hardware but software. So again, this is another layer of complication. I'm not even talking about physical inputs, the basics between the human connection, but a lot of these systems are in place to also move forward the autonomous driving functions and safety functions in cars. Now, the next discussion is software evolution. This is extremely important inside of cars. And you could have software that's built by the manufacturer, you could have simulation tools, you could have AI tools that help do coding and debugging and speeding up the process for engineers. But the bottom line is the software and the hardware is only as good as the engineers that have worked on them and have a strong knowledge base. And this is more important in performance cars or enthusiast cars. And one of the big issues with modern vehicles, and as we move generationally forward, I grew up with the analog tech and the digital revolution. So I knew what cars were like in their peak when they were just not electromechanical, just pure mechanical cars. So I have a basis of getting inside a car and like an older car and feeling things. Like, I got into a Miata recently and I was like, is there something wrong with this car? And I realized there wasn't. It was just because there was feel through the steering wheel. You could feel things through the brakes and throttle pedal in some cases. And it's a weird sensation when you're actually getting feedback from a car, and you come to the modern cars and they don't have that anymore. They've literally been isolated out a lot because of the hardware in the cars and the way that the cars are manufactured now. So at some point, you're going to get next generation engineers that have no basis for comparing the old cars. And unless the manufacturer, the brand that's training them, requires them to drive some of these older cars for reference, or they go out on their own and really drive everything, which is a lot harder to do these days, you're going to get more and more cars and more philosophies of throwing away the old and really only focusing on the modern technology. So the other side of this is The older cars, and one of the reasons why I said this at the beginning is that I'm so conflicted. When you got into some of these like late 90s cars and 2000s cars, they were delivered to you when you bought them at the dealership or when you bring them home, they were done. You know, they were literally hard coated. There was no fixing it later, no changing anything, because everything was mechanical and it had to be right. Now, not every car was great, right? Obviously, there were still problems or mechanical issues, but on this, they didn't have to worry about the software, which leads into the connected car discussion. Every single car now, almost every single car, has some type of connectivity to the internet, telematics. Some of that is for data logging purposes, some of it is so they can do diagnostics, some of it is so they can improve cars over the air or fix problems that they couldn't get done when the car rolled out. And it's a blessing and a curse because of the software I talked about and how complicated these cars are. The last thing you'd want is to roll out a car with some major software issue that you couldn't fix and you'd have to recall every single one of them. This gives the manufacturers the flexibility of not only improving certain functions or actually fixing things on the software side, even if there might be a mechanical component. So it gives them a lot more flexibility of kind of keeping the cars relevant and improving them as they go. The negative part is that typically hits the customer. And I'm not even going to get into the discussion of the engineer's thought to replacement of parts, longevity of parts, and repairability. That's a discussion for another video. Now this is the big one, and this is an argument we've had with many brands and engineers, and some of it's gotten pretty heated, and we get this from the viewers like you who constantly ask us why. Why is this necessary? And I think there's some components of humanity and engineering where you start to reinvent the wheel and you start mucking with things and messing with things that were never really broken to begin with. When we talk about the physical inputs, I had this discussion with the Corvette engineers, Jack had it with Ferrari, and we talked with Lamborghini about this. And I would say that there is an agreement that when you get inside a car, there are a slew of things that you're interacting with every single time you drive. And from the enthusiast side, you want to be able to feel what's going on the steering wheel. You want it to be natural, like you're actually turning the wheel and the car's responding. You want the pedals, the brake, and the throttle to feel like they are really one-to-one to your inputs, that they can communicate back to you what the car is doing. And when you decouple the wheel and the pedals from the car physically, where you're no longer having the muscle memory of having a mechanical linkage and you're doing it all through software, there is fallout to disconnecting the driver or making it variable, right? We're super sensitive as people to subtle changes like spikes or changes in things. And that's something that we've noticed more and more in modern cars. I just got out of a brake-by-wire Cadillac SUV, and the pedal, because the brake pedal is just on a spring-loaded mechanism, right? You push it down, it feels super firm, and it's the same every time. But what I'm pushing down on the pedal doesn't equate one-to-one with the braking force of the car. It doesn't matter how hard it feels, the car continues to slow down at a slower rate than what the pedal feels like. And this is a disconnect with a lot of these electronic systems. Same thing could be said with steering. Companies like to mess with the effort. They give you motor assist to tighten it up where it's harder to turn the wheel or less hard to turn the wheel. Some steering systems have variable gear ratio where you turn it a little bit at first and it's quick and then it slows down after. These variable inputs that they're putting in more cars make everything more vague and hard for you to get connected with them. So really, the point of this video is why cars are feeling like simulations is because of that software part, that they're able to manipulate each one of these physical connections to the car and alter it digitally because they're no longer real. You know, your pedals are no longer connected to something physically. It's an emulation. So when I'm talking about simulators, and this is going to be our future project here, is I built a sim rig and I'm going to be working with the brand's simulators that they're using to develop cars. Because believe it or not, a lot of these brands are now using driving simulators or driver in the loop to help them understand how to load things in on the software level during development. So tire models, right? Let's say Bridgestone gives a brand a tire model. This is what it's going to feel like. This is how the cars are going to respond to these digital systems. They can load the tire models, all the grip levels, the sizes into the simulator and have a general feel of how the car is going to respond, and all the electronics are going to respond to that tire. The same thing can be done for brake evaluation or noise levels. You can kind of simulate tire noise or road noise and all the things that you're going to feel in the car. You can also play with pedal forces. Now that pedals are largely digital, you can load in your throttle mapping, the control side of the throttle mapping, and what different modes do to how you push down the gas and how the car responds, or in electric cars, how much torque you're getting, how much head snap, what happens when you lift off a pedal, how much decel you get. All of this can be loaded into a simulator. Now it's time to talk about hardware. A lot of people get hung up with this on the internet and they like to flex about what they have and they don't have. That's not what this is. I'm using tools specifically to be able to interface with engineers from multiple brands to understand and explain how these systems work and how the digital domain is so important to physical car creation. So the first company I'm working with, as I mentioned, is SimiCube. I'm going to work with their engineers to explain how their active pedal system works, which you can go into any car, like a Porsche GT3 or a Honda Odyssey. I can do measurements of the pedals, feel, pressure, linearity, depth, and the active pedals from SimiCube can literally emulate that. You can make them to feel the same through their software tuning. So you can adjust their software to create pedal profiles for every single car, which is extremely helpful if you're trying to test car models, right? You want to have a specific one for each car so it feels more real. They've also been able to emulate things like ABS actuation points and vibration. These are very high-end systems that I think even manufacturers are struggling to figure out how to get feedback back to the driver, and they're able to do it in the digital domain. Now, Falcon PC is also helping with this project. They have supplied some of the best workstations, physical workstations, towers that I've ever used, and they are going to power the simulator that I'm using and my editing rig. Now, because I've moved everything off cloud-based infrastructure, people talk about data center utilization, I'm moving everything on my PC. From generative AI, generative models, editing, audio editing, all of that's done there. And the simulator is also going to be powered by that in all the models. Now, the primary Falcon workstation I'm going to be utilizing is powered by a 64-core AMD Threadripper, a 9980 series. And this is different than a regular consumer CPU. And large part is it supports error checking RAM, or ECC memory, up to 1 terabyte. And of course, I didn't win the lottery, so mine only has 256 gigs of memory, and I'm utilizing all of that, believe it or not, for the editing and a lot of these modeling things that I'm doing, and not my own personal modeling, computer modeling. And the other thing that it does support is Gen 5 SSDs. Because of the architecture of the board and this setup, you can run multiple Gen 5 SSD drives and a Gen 6 graphics card simultaneously. So really, as a single user, right, where I'm not running a server farm, and again, I don't want to run anything on the cloud as much as possible, I'm able to bring a lot of this stuff in-house. And having that AMD support, having Falcon support us on this project, having SimiCube engineers, and of course the manufacturers to explain how all of these complicated systems work is going to make this for a really interesting series to learn from some of the best people in the industry. So hope you come back, subscribe to check out these future videos. I think, if you're into technology like I am, you're going to love it.